Welcome back, and in this video we'll be looking at the software and hardware aspects for our mechatronic system. So we'll just start with some definitions. So what we'll have is we potentially have two computers we need to think about. We have got our development computer, and this is where we write our programs and potentially compile them into something machine readable. So this is typically your laptop, desktop computer. So what we do is we write our program here and then we upload it to what's called the target computer or the target microcontroller. And this will be where the program actually runs. We have a compile time. And when we write our program, this will need converting into something that the computer can understand. So this is known as our compile. And this translates what's called the source code. So this is what we write our program into something machine readable. If there's any errors at this stage, then these might be detected by the compiler, and these are called compile time errors. So when the computer compiles this into a runnable program, if there's any apparent errors at this point, the compiler will notify you. And these are typically syntax errors. So, for example, if you forgot to include a semicolon at the end of the line. These are quite easy to find because the computer tells you there's a mistake and roughly where it is in the program. So you can track this down and correct it. When you've uploaded it to your target computer, you're then at runtime, and this is when the program is running and the system is actually operational. If there's an error at this point, this is known as a runtime error. And these are very difficult to track down because you don't know where in the program this error is actually happening. So these are very hard to spot and very hard to correct. So it's just a warning that compile time errors you can find fairly easily and you can correct them. If it's a runtime error, these are a lot more difficult to find and correct. So the program itself on your target computer will look something like this. So this is probably what the program will look like. It's just a series of values. In this case, these are essentially binary numbers. On this PowerPoint slide, they're represented as hexadecimal. Just makes it a bit more concise to read. But this is essentially what the computer needs to understand. It is impossible or very difficult for us to actually understand this, so we need some easier language to write our program in before it gets converted into this form. This is the final stage of compiling, so you don't actually see the program in this state. We'll see it in a much more readable state, but once it's compiled, it will be then in this state, which you then upload to your target computer. So I mentioned that last slide was in hexadecimal, so that is base 16. Computers do work in base 2, which is binary, which is 0 or 1, and we tend to work in base 10. So we count 0 to 9, and then next place is 10. So we're used to base 10. Computers need base 2, and to be if we want to program in binary, we usually use the format of hexadecimal, which is essentially binary, just a bit more concise. So that is base 16. So you might have when you write a program, you can represent numbers in any of these formats. You just need to be sure you can convert between them. So in this case, as an example, we have got the number A2 in base 16. So in order to convert that into either binary or decimal, the 2 is essentially 4 bits. So the 2 is our first 4 bits here. And then the A in hexadecimal, A has the value of 10. So we can write that as 10 in binary, 1010. So A2 becomes this value in binary. We can convert that into base 10. So we could convert this binary number into base 10, which gives us 162. Or we can convert it directly into base 10, because we know this place here is essentially a 16 to the 0 place, and this place here is a 16 to the 1 place. So our 2 represents a value of 2, and our A represents a value of 10, which is here, but that is the second place along, so that is a 16 to the 1 term. Okay, so as I said, you can represent numbers in your program in any format you wish. You need to define the format when you're programming it, but you can program in any base you wish to, whatever is convenient. But be sure you can convert numbers between bases, so you actually understand what value you're actually using. Okay, so in terms of languages, assembly language is the lower level language. So this is the closest to an actual computer understandable language that we can realistically write to. And these are essentially just single instructions for the computer to run. So for example, you might have the command LDA hash $C0, and that is a single command for the computer to perform. In this case, it's known as load accumulator. So it's actually taking a value and placing it somewhere in memory. So this is not quite the same as the assembly language, which was all just values. This uses mnemonics, so it kind of is a bit more easy to read. So the LDA in this case is load accumulator, and ADC mnemonic is add and carry. So this machine, it is human readable, but it is sort of quite specialized. So it is possible to code in this in assembly language. A lot of people do. It's the best for runtime speed because it's so similar to the actual final language what the computer is going to read. Then it's essentially a direct mapping. Whatever line of code you write here, this translates directly into a line of code on the computer. So because of that mapping, then it's optimized for run speed. In terms of development, so how long it takes to write these programs and modify them, it is quite slow in that respect, because it is sort of it's not easy to read this, so you really need to understand what you're doing. So if you want speed and not so much concerned about how long it's going to take to develop, and particularly if programs are very small, then assembly language will be the option. For most of us, however, we tend to use high-level languages. So assembly language is known as low-level. High-level languages are a lot more readable and easy for us to understand. And most of the languages you will come across are classed as high-level languages. So the common ones are C, C++. So this is probably what you're familiar with. And we've got Python, Java. There's a whole range of languages out there. So they're easy to code. Especially for large projects, because the code itself is fairly sort of understandable. So for example, a print statement means you're going to print something on the screen. So it's easy to read what the code is and know what's going to happen. So in that respect, it's good for big projects and it's good for development work. The downside is the translation. So it needs to be translated into computable readable form. And there's two aspects of that. One is the speed and one is the overhead, or the memory overhead. So when it translates it, although it's easy for us to read, it might actually take more lines of code to translate it into something readable by the computer. So in that respect, it takes up more memory in the computer, and it's also slower to run. So that's the downside compared to assembly language. However, some of these work really fast, so you don't really notice the difference. Because the hardware these days is so quick, then writing a program in C, for example, there's not going to be much apparent change in speed compared to writing it in assembly. So don't feel you're limited by these languages. They still give very good performance. Some languages are better than others, and that's mainly because whether they are interpreted languages or compiled languages. Interpreted means that when the program runs, it takes one line, translates it, and then runs that line of code. So it's converting the program as it is running it. On a compiled language, it translates the whole program firstly into what the computer needs, and then use that compiled version. So compiled programs run a lot quicker than interpreted languages. So when you choose a language, there's a few things to think about. Most important is it available? So given you've got a certain computer system there, is that language available on that computer system? Speed is important. So if speed isn't an issue, then you might be able to get away with something a lot more simple to understand, but just run a bit slower in terms of programming. If speed is important, then you want a fast language such as C, for example. Memory overhead. So if memory is very tight, then your program has to be very sort of well written to make use of the memory available. So this could be in C or, for example, assembly language. So it depends how much memory you've got to play with. So that's something you need to consider. Size of project. So I said a small project. If you want to write an assembly, a program in assembly, then you're probably looking at a very small program. Anything that is an appreciable size, you want something a lot easier to read. And if it's a program where there's several people having to work on the program, then again that has to be easy to read, so different programmers can understand what each other are doing. From a personal point of view, learning curve. So if you already know a language, it's going to be a lot easier to use that language in your system compared to having to learn something new. So that's from a personal point of view. And the libraries and support available. So again, if you're using a language, what other support do you want out there? So some languages are supported better than others, and libraries are available. So when I say libraries, pre-written code that you can use. So that is something to bear in mind as well, what support you have in helping you develop these programs. And then finally, future maintenance. So you'll write something and then use it, but your system might need some changes in the future. So how easy is your program going to be for somebody else to look at that, understand it, and change it? So that is something you should bear in mind. So that's the software side of things. In hardware, in terms of hardware, you can use, there's lots of options for what kind of computer you want on your robot or your mechatronic system. So there's a few listed down here. And the first thing you want to think about is, do you want it to be real-time, a real-time system? So when I say real-time, it actually does things. You can predict exactly when it's going to do something. So you know one line of code might take a certain length of time, a microsecond, next line of code, a microsecond. So you know exactly how long each line of code takes. This is what's known as a real-time operating system. And you know things are going to respond when they're supposed to. Non-real-time systems is when the computer might divert its processing power to do another job and sort of leave your program for a while and come back to it. So, for example, if you're using a Windows machine, you might be typing something into the keyboard, but your keyboard strokes are not recognized because the computer is doing something else, might be running some virus software or something, and then you see your keyboard strokes updated within 2 or 3 seconds. So it's not a big delay, but there is a delay there, and that's not a real-time operating system. So you need to consider whether real-time is essential for your job you need to do. So in terms of the computer options, microcontrollers. So these processors, they work real time, so you can predict them, but they are limited specs. So they are very cheap. So good for things like for mass production products, but they have got limited specs, so they've only got limited applicability. Computers, so we all know what computers are. Lots of processing power available. The main difference between a computer and a microcontroller is the computer has got the user interface. So a computer, you can plug a keyboard in, you can plug a mouse in, you can plug the computer itself into a monitor to see what is happening, you can write programs on it. Microcontrollers, you cannot do that. Microcontroller, you need a computer to write your program, see what's happening, and then upload the program to the microcontroller. So that is the main difference. But computers, generally speaking, good processing power. So they got they can do a lot of number crunching. They got the user interface. A lot more expensive. A computer is a lot more expensive than a microcontroller. But they don't multitask. They multitask, so they're not real time. Because they're multitasking, because they're doing lots of jobs at once, they're not real time systems. I've mentioned FPGAs there, which I'll come back to in a little bit when I mention a specific system. Not very commonly used at the minute. They're becoming more popular, but I'll just mention that in passing. Now, I don't want you to feel limited by you've got one choice and that is it. So a lot of systems today have got multiple processors on there. So this is an example of a student project from a couple of years ago. So he built a robot. It was artificial intelligence to perform some navigation. So that was the project. The student first had to build the robot. So this is the robot he came up with. As you can see, we've got two processors on there. We've got an Arduino, and that was to do the real-time stuff. So that was to control the motors. So controlling motors real time and doing some sensor information. There's also a couple of cameras on this robot, and because the processing needed to process an image, then an Arduino isn't suitable for that. So we had a Raspberry Pi computer to actually look at the processing of that. The two processors, so the Raspberry and the Arduino, were connected to the serial comms, so they spoke to each other. But the Arduino was the main controller for the robot, and he took care of most of the real-time handling. And then the Raspberry was used as a secondary processor to do some of the data processing. Okay, so as I said, don't feel limited that you have to choose one and stick with that. You can have multiple processors, computers on there doing specific jobs, and you sort of get the benefit from the strengths of each. So in terms of hardware, I've said there's microcontrollers, computers, etc. Within that, there's a lot of choice. So we'll look through a few examples. So we'll go through these examples. There's a lot more than this. So I'll refer you to this web page. It's a few extra examples, but there's a lot to choose from. So excuse that the microphone just fell over. Right. So in terms of options for hardware, so we'll start with what you'll all be familiar with, the Arduino. So the Arduino is a microcontroller. So it's real time. There's lots of different options. So you might have come across an Arduino Mega. So this is the Mega. The recent instrumentation and drives module used an Arduino Uno. So they're all very similar. They've got the same processor, and they've got different amounts of memory, different amounts of input pins. So the Mega is the top end version, so it's got lots of input options. around here. It's got the 256K of memory and an option of input pins. It's programmed on a desktop computer, and it's got an IDE, so a programming environment to do that. So it makes programming compiling fairly comfortable for a user. So Arduino is your entry-level type of processor, so it's an easy way to get started into programming. As I said, there's lots of different options. So if I refer you to this web page, you can see the different types are available. So they come in various sizes, number of digital pins, etc. Next option I'll discuss, Raspberry Pi. So this is what's classed as a single board computer. So because it's a computer, it's not real time. It'll be multitasking. It's a lot more powerful than your Arduino microcontroller. Again, there's a wide range of options available. So you can get different sizes depending on what physical sort of requirements you have, or geometric limitations you have in your system. So there's lots of sizes available, different memory options, etc. Current version, so the current top of the range is version 4 with 8 gigabytes of RAM. It has a 4K output for a monitor, and it's got USB 3 input capability. And it also comes with a wireless option. So unlike the Arduino, it can connect directly to the network without any additional hardware. The hard drive for this is a micro SD card. So that gets plugged in, and that is essentially your hard drive for this computer. Because it's a computer, it needs to run on an operating system, and this is done with Linux. So you upload an operating system to your SD card, and it runs on that. You can choose any language you want, so you just load whatever programming language you want onto the operating system and program in that. So the commonest one for the Linux, for the Raspberry, is the Python language, but you're not limited. You can use C, for example. One notable difference between the Raspberry and the Arduino, it's got no built-in digitizer. So if you want to do if you've got an analog signal and you want to digitize that, then you will need to buy additional hardware in order to do that. The Arduino has got that built in. Next option, BeagleBoard. So the BeagleBoard is very similar to the Raspberry Pi. It was produced by Texas Instruments. It's slightly lower specs than the Raspberry Pi. So in that case, the Raspberry Pi is sort of a bit more of a powerful computer. The BeagleBoard was brought out for sort of such applications as robotics and that. And its main strength was the capes, or the boards you can plug into it. So when I say capes, if I just go back a little bit, each of these boards, so each of these, you can get additional hardware that plugs into the computer or the microcontroller itself to give it additional functionality. So for example, the Arduino, you can get a motor shield, and what that is essentially a H-bridge that you can plug this board onto the top of the Arduino, and then you've got this motor driver capability. So a lot of the available computers and microcontrollers come with these. For some reason, they call them different things. So the Arduino, they call shields. On the Raspberry, they're called hats, and on the BeagleBoard, they're called capes. But they're all the same thing. It's just additional hardware that you plug in, and they can use that capability. So the strength originally of the BeagleBoard was it came with many capes. So you can just plug this hardware in, and then you've got that capability. So that's what made it popular in the early days. But there's a lot of third-party companies out there now that supply additional parts for Raspberry, Arduino, etc. So there's lots of these shields, capes, hats, etc. are now available for all these systems. Right, I'll mention National Instruments here. So this is slightly different. This is a field programmable gate array, so I said these are becoming more popular. And what these are, it's essentially a computer, but these are a series of switches, so you have to program them. Well, you program them on a computer and then upload them to the FPGA. But the power in this is that because these switches, the program's not running sequentially. So when you have an Arduino, you run one line of code and then the next line, etc. So each line of code in an Arduino is ran one at a time. In FPGA, these can potentially all run simultaneously. So you have sort of true multitasking capability here. So that means they are very fast. So with that comes the expense. So these are certainly the LabVIEW one. You're probably looking at a few £100 for this. So they're more expensive, and you've got to sort of learn the FPGA programming and that. So there is some overhead in the learning curve. LabVIEW has got an option of LabVIEW called LabVIEW Real Time, LabVIEW RT, and this allows you to program this board using the LabVIEW language. So it is an option. We have got some at the university. As I said, it's very good for if you need the speed, real-time speed in your system. And some of these boards were used when we were first developing driverless cars. So some of the initial projects were using things like your LabVIEW FPGA boards to actually perform these tasks. So they are potentially very powerful if you need that. On the other end of the scale is microchip. So these are microcontrollers. Now, if you look at the Arduino, if you take an Arduino, the Arduino is a microcontroller, which is this microcontroller, the 18 meg. And that's been packaged up into a PCB and had an interface developed for it so you can program it. The microchip's essentially exactly the same. Essentially, you just buy these in chips form. So you would get a chip, something like this. You can get boards to plug them into, and you've got an interface to program it. So in that sense, they're exactly the same. Very cheap, a few pounds, come in lots of different ranges. You can get very basic ones to very complex ones in terms of the very fast, got good memory for things like digital signal processing. So there's a whole range of microchips available to use, and you typically use these for something that is sort of a bit of a smaller scale. So you wouldn't potentially control a whole robot with this, but for example, you might use one for, say, on a wheel assembly where you want to do closed loop PID control to maintain the wheel speed. So something like this would be ideal for that. And then you have a more powerful processor to actually control the main job of the robot. So similar to the MSC example, you can use lots of different systems or lots of different controllers on your mechatronic system. So potentially this is where the microchips and such technology would come in. So there's lots of different options available. So again, I don't want you to feel limited by what we'll be using in this module. And certainly in terms of your projects, you can use any of these options available if you want to learn something different. For this module, we'll stick with the Arduino. As I said, it's a good entry level. You've got experience from previous modules using this, so we'll stick to the Arduino. It's easy to write code. Offers syntax highlighting, as that makes it easy to program. So it'll highlight different sort of aspects of the code, so makes structuring easy. And there's lots of useful resources for it in terms of examples, etc. So it's a very good place for us to start. In terms of the programming language, we'll be using the high-level language C. So the Arduino is based on C, C++. So it's high level. It's good for our small projects, excellent for large projects. So this is what we're doing here. So it's applicable to our full range of things, what we need for this. Good for cooperative work. and it's sort of very common, so there's a lot of resources available for it. So for this module, we'll use the Arduino, the C programming language, to actually do our work. Now you've all come across the C before, so instrumentation and drives. Some of you had an introduction to Arduino and C, others of you are more familiar with it. So what we'd like to do in this module, and we'll continue with that, but let's try and take it up a level, so just a bit more in terms of better programming, etc. For this module. So there's two aspects. So you've done your Arduino programming and you've written programs in it. So we're continuing from that, but for this module, I'd like you to think a bit more about writing functions. So rather than writing one long block of code for your program, separate it out, write it as functions. Functions make the code a lot easier to read, structured and read and understand, but also with having functions, these functions can be sort of utilized by other programmers, for example. So it makes it a lot more interchangeable between programmers. Okay, so you'll be using a lot of libraries, a lot of other people's examples, a lot of classes, etc. So by doing, you need to learn how to sort of write your functions for yourself and do that. Okay, so one aspect of this programming in this module is better structure in your Arduino programs, and the second aspect is kind of trying to optimize your code. And one way to do this is looking at variables and sort of using variables or defining them so they're optimizing the code. So what we'd like to do with variables is two things. Firstly, limit the amount of space they actually need. So if you want to store a number in a variable, only have that variable the size you need it to be. So I'll come on to examples of that. And also, where is that variable visible? So the easiest thing to do is just make everything global, and then everything's accessible right through the program. And that's not the most efficient way of programming. It's better if only one function is using a variable, for example, then that variable should only be defined in that one function. Okay, and creating structures like that, and very limiting the where variables are actually seen and stored, etc., does improve your program. Okay. So as an example of that, let's consider these numbers. So we've got the number 23, 46023, 23e to the 12, the letter Z, and a string of letters. Okay, so if we want to store each of these numbers, we need to think about what size each of these numbers needs to be. So the best way to do that, if I escape this, is go onto the Arduino reference website. Now the first number we needed to consider was 23. So we've got these different options. If I look at byte, and click on here, byte is a number, you can store a number anywhere between 0 and 255. So it's 8-bit unsigned integer, so it's going to be 1 byte long, 8 bits, and you can store any number in that range, 0 to 255. So our best option for storing 23, number 23, would be a byte. The number 46023, so that is an integer number. So if we go on to the integer website, or the integer reference page for Arduino, we find integer on an Uno. So if we're using an Uno, it's 16 bits, 2 bytes. What 16 bits gives us is the range of minus 32,768 to plus 32,767. So in terms of our number, that is outside the range, so that is no good in that respect. Okay, so an int isn't going to be within the range we need. If we look at long, long is from minus 2 million to plus 2 million. So we could actually define our value of 46,000 as a type long. We've also got another option. Long is actually 4 bytes long. Int is 2 bytes, but we said int isn't big enough. However, if we know our number is always going to be positive, then what we can do is say this is an unsigned int. And an unsigned int, rather than go from minus 32,000 to plus 32,000, will be a range of values from 0 up to 64,000. And the advantage of using an unsigned int is it's only 2 bytes rather than 4. So we're actually halving the amount of memory we need to store this number. Okay, so given we've got our numbers, we can use the reference page and decide what is the optimized way of storing this. So number would be a byte, or 23 would be a byte. The number 46023, typically you would think of it as long, but if that number is going to be between 0, if that number isn't going to be, is always going to be within the range 0 to 64,000, we can actually use an unsigned int, which would actually just be 2 bytes long to store. So it's a lot more efficient in using the memory. So if you continue with this exercise, we'd find the number 23.51e to the 12 to be type of float. The letter Z is a character. It's also a byte. So if you look up the ASCII table, the value of Z is 122. So any single character is going to be in the range of 0 to 255. So any character can be classed as a byte or it can be classed as a character. We've got a series of characters here. In the last example. So that is a character string, an array of characters. So we can define an array of characters as character with our square brackets, and that defines it's going to be a list of characters. And there's also a special function or class called string in Arduino, which has been written. So again, we can represent that as a string. Okay. So the point of this is, as I said, you've had programming practice with the Arduino. For now, now when you start a program, I'd like you to think about more using functions, better structure in your program. And when you're using variables, only use them in the functions or the parts of the program where they're needed. So give it better structure, and also try and limit the range. So when you declare these variables, try and limit the range of them to actually what's needed. Okay, because that's then saving you memory, and it'll sort of optimize the speed. Okay. So that's just something to think about to take your programming to the next level, sort of improve on your programming skills.
In the final video of today, we will consider the mechanical engineering aspects of our mechatronic system.